Let's think about this for linear regression of polynomials. So let's look at a linear regression problem. All right. So suppose I've got some points here, okay? And I would like to find a line that best approximates those data points, all right? So what I really want to do is find a line that minimizes the distance between the points and the line, all right? But the way to think about that is if I want to find the line, right, then I'm going to have x's and y's. So I have x1, y1. This could be x1, y1. This could be x2, y2. This could be x3, y3, and so on, okay? So, and those will just be values. Well, what I want to know is, I'd like to know m, I'd then like to know b, since the y equals mx plus b. I need m and b. And what I really want, right, is I want to find an m and a b. It would be great if m and b satisfied every equation, but there's going to be lots of equations. It won't be the case that they satisfy those, so we can go after this with least squares. I'll write this a little nicer. So you're going to get y bar is equal to, I'm going to kind of separate it out like this, and then I'm going to put my column vector here, b and m. So if it's b, then this is 1, right? 1 times b, and then m is just x1, x2, x3, x4, and my y is going to be y1, y2, and so now I have a ax equals b form here, right? And we can apply least squares to that. So let's look at the example here. So now I've filled in our points here. So now my matrix A is 1, 1, 1, 1, and then the x values -1, 0, 1, and 2. And B is going to be my y values, 0, 1, 3, and 9. So go after our normal equations. A transpose AX hat, A transpose times B, solve that thing for X hat, and I get this, which in this case is going to be B equals 1.8 and M equals 2.9. So that's Y equals 2.9x plus 1.8 is my least squares solution, and that's a line that best approximates those 4 points. It minimizes the distance between the line and all of those points. Okay. Now, so here's my, I actually drew it in here, y equals 2.9 plus 1.8. Okay. Now, we can do more than that, right? So there's no limit to what I can do here. So I can actually put this, A is my design matrix. All right? So I can let it be 1. So if I wanted to do y equals c1x plus c2x squared, then A would be x1, x2, x1 squared, x2 squared, x3 squared, right? If I wanted to do, in this case, let's do y equals, I'll do it with c's, y equals c1 plus c2x plus c3x squared, right? Then the first column of my design matrix goes with the c1, and that's always just 1, right? Second one is c2 with x, so there's just my x values. The third column is going to be x squared, So I just put in my x squared, minus 1 squared is 1, 0 squared, 0, 1 squared is 1, 2 squared is 4. And my b's are still all my y values. So now I use, for the same data points, did I use the same data points? I think I did. For the same data points, I'm now going to do the least squares solution. And I get this. So now I get a polynomial. And it happens to be that this is sort of a perturbed polynomial. You notice the fit's a little better to the points when I graph it. All right, so you can do as many degree polynomials as you would like here. Now, you need overdetermined systems, and typically if you get into higher order polynomials, you start to get polynomials that do a lot of this. So not often not good. Typically linear approximations are by far the best. Okay?